And we have engine start. James Webb begins a voyage back to the birth of the universe.
Evidence from the field of astrobiology implies that life in its most basic form can be found virtually everywhere in the universe. It has most likely occurred several times in our own solar system. However, proving the presence of human-like, technologically advanced life forms is a much more difficult prospect. It all comes down to solar energy. The first simple life on Earth probably began underwater and in the absence of oxygen and light, conditions that are not that difficult to achieve. And humans have long speculated what life may be like on distant planets. This question can now be answered owing to the James Webb Space Telescope, the most powerful telescope in existence. The first clear evidence of carbon dioxide in the atmosphere of a planet outside the solar system has recently been discovered by NASA's James Webb Space Telescope. This observation of a gas giant planet 700 light-years away in the orbit of a sun-like star provides critical information on the planet's composition and evolution. After this discovery, NASA Administrator Bill Nelson promised that humanity will soon have a wholly unique view of the universe, unlike anything we've ever seen before. So today, we'll look at the latest James Webb Space Telescope discoveries and analyze what it means and what else is out there. The James Webb is outfitted with two infrared cameras. The first is a near-infrared camera, often known as a NIRCam, which records shorter infrared wavelengths. The second device is a mid-infrared camera, commonly known as a MIRICam, which records longer infrared wavelengths. The images exhibit a variety of unique characteristics based on the camera that was used to capture them. So far, NASA has released a slew of images captured by this gigantic, one-of-a-kind telescope, and they are, to put it frankly, amazing. Stars emitting spectacular blue and orange light, galaxies whirling and crawling around one another in a tangle of stars and dust clouds, and some of the universe's oldest light emitted 13 billion years ago. So far, the data collected looks to be safe, but you never know when things will change. After all, NASA anticipates that this telescope will be able to view light from the universe's farthest reaches, which might be as dangerous as it is exciting. And recent NASA findings have academics and researchers all over the world delighted. Last month, an international team of astronomers using NASA's James Webb Space Telescope collected an in-depth inventory of the deepest, coldest ices yet observed in a molecular cloud. The team was able to identify frozen versions of a wide variety of molecules from carbon sulfide, ammonia, and methane to the simplest complex organic molecule, methanol, in addition to simple ices like water. This is the most complete census of the ice components available to make future generations of stars and planets before they are heated during the birth of newborn stars. This image from the telescope's near-infrared camera shows the center part of the Chameleon-1 dark molecular cloud, which is located 630 light-years away. The brilliance of the young outflowing protostar CED 110 IRS-4 illuminates the chilly, wispy cloud material in the infrared. The light from several background stars, visible as orange dots behind the cloud, can be used to detect ices in the cloud, which absorb starlight as it passes through them. This study was part of Webb's Ice Age project, one of 13 early release science programs. These observations are intended to demonstrate Webb's observing capabilities and to teach the astronomical community how to get the most out of its instruments. The Ice Age team has already planned additional observations, with the goal of tracing the evolution of ices from their formation through the production of icy comets. Just 1 week before this discovery, JWST imaged the inner workings of a dusty disk surrounding a nearby red dwarf star. These observations represent the first time the previously known disk has been imaged at these infrared wavelengths of light. They also provide information about the disk's composition. The star system in question, AU Microscopii, or AU Mic, is 32 light-years away in the southern constellation Microscopium. It's about 23 million years old, which means that planet formation has ceased, as that process usually takes less than 10 million years. The star has 2 known planets discovered by other telescopes, The dusty debris disk that remains is the result of collisions between remaining planetesimals, a more massive analogue of the dust in our solar system that cause a phenomenon known as zodiacal light. AU Mike was studied using Webb's NIRCam. Scientists were able to analyze the region very close to the star using NIRCam's coronagraph, which blocks the bright light of the core star. The NIRCam images allowed the researchers to trace the disk as near to the star as 5 astronomical units, 460 million miles, the equivalent of Jupiter's orbit in our solar system. The observation program captured images at wavelengths of 3.56 and 4.44 microns. The scientists discovered that the disk was brighter at shorter wavelengths, or bluer, implying that it includes a lot of tiny dust that is better at scattering shorter wavelengths of light. This discovery is consistent with previous research, which revealed that the radiation pressure from AU Mike, unlike that of more massive stars, is insufficient to eject fine dust from the disk. While identifying the disk is crucial, the team's ultimate goal is to hunt for massive planets in broad orbits such as Jupiter, Saturn, or our solar system's ice giants. These worlds are extremely difficult to discover in the vicinity of distant stars using either the transit or radial velocity approaches. In another discovery, an asteroid roughly the size of Rome's Colosseum, between 300 to 650 feet, 100 to 200 meters in length, has been detected by an international team of European astronomers using Webb. Their effort made use of data from the calibration of the mid-infrared instrument, MIRI, during which the team discovered an interloping asteroid by chance. The object is likely Webb's tiniest to date, and it could be an example of an object measuring less than 0.6 mile, 1 kilometer in length within the main asteroid belt, which is located between Mars and Jupiter. More observations are required to better characterize the nature and features of this object. These Webb observations, which were published in the journal Astronomy Astrophysics, were not intended to search for new asteroids. Rather, they were calibration photographs of the main belt asteroid 10920 1998 BC1, which was found in 1998. The observations were carried out to evaluate the performance of certain of MIRI's filters. However, the calibration team determined that they failed due to technical issues such as the brightness of the object and an offset telescope pointing. Despite this, the scientists used the data from asteroid 10920 to develop and test a new technique for constraining an object's orbit and estimating its size. The method's validity was established for asteroid 10920 by combining MIRI observations with data from ground-based telescopes and the ESA's Gaia mission. During the MIRI data analysis, the team discovered the smaller interloper in the same field of view. According to the team's findings, the object is 100 to 200 meters in size, has a very low inclination orbit, and was located in the inner main belt region at the time of the Webb observations. The discovery of this asteroid, which the team believes is the smallest observed by Webb to date and one of the smallest detected in the main belt, would have significant implications for our understanding of the formation and evolution of the solar system if confirmed as a new asteroid discovery. Current models predict the occurrence of asteroids down to very small sizes, but due to the difficulty of observing these objects, small asteroids have been studied in less detail than their larger counterparts. Astronomers will be able to study asteroids smaller than 1 kilometer in size in the future thanks to dedicated Webb observations. Furthermore, this finding suggests that Webb may be able to contribute to the discovery of new asteroids by chance. The team suspects that even short MIRI observations close to the solar system's plane will always include a few asteroids, the majority of which will be unknown. With all of the discoveries the JWST is making every day, it is reasonable to wonder, will it find life on any other planet or exoplanet? Since the dawn of civilization, humans have speculated about whether or not there is life elsewhere in the universe. There were no known planets outside of our solar system 20 years ago, but since then, over 4,000 additional planets, also known as exoplanets, have been discovered orbiting other stars. According to NASA, the cosmos could be home to trillions of exoplanets. Extraterrestrial plant life may include the earliest traces of life beyond our solar system. When the Galileo spacecraft was on its way to Jupiter, it turned its instruments back towards Earth and discovered a clear sign of the presence of plants. The vegetation red edge (VRE) biosignature was discovered by the sensor as a combination of red and infrared lights reflected by plants. For example, a plant covered with rainforest, such as Earth, should have a strong and easy-to-detect VRE signal. The JWST will measure the VRE of distant Earth-like planets in the habitable zone near stars. They might be significant life signs in the exoplanet's atmosphere. When sunlight passes through the star of a planet, the JWST may be able to detect it when it enters its atmosphere. The missing wavelengths of light would subsequently be detected via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a unique fingerprint that the JWST can detect. This method can be used to determine the makeup of the atmosphere and whether or not life exists. Life is expected to exist on Earth-sized planets with atmospheres similar to ours. Proxima Centauri, a red dwarf star 4.25 light-years from the Sun and our nearest star, provides the best opportunity for humanity to observe city lights outside the solar system. Because Proxima is around 600 times fainter than the Sun, a planet must be 20 times closer to it than Earth is to the Sun in order to host liquid water-based life. In this habitable area, scientists detected a planet with a mass of 1.3 Earth masses in August 2016. Proxima b circles Proxima Centauri in a Goldilocks-like habitable zone where the light intensity is just right to melt water. Given that it surrounds its red dwarf star Proxima Centauri at a distance of only 4.6 million miles, Proxima b could be an airless dead planet. The Sun and Earth are separated by 93 million kilometers. Proxima b is in a tight orbit, exposing it to powerful solar winds that can entirely destroy its atmosphere. It also delivers enough sunshine to maintain Earth-like temperatures and liquid water. Due to its close proximity to the star, Proxima b is thought to be tidally locked, always showing the same side to the star as the Moon does to Earth. Proxima Centauri has roughly 1/8 the mass of the Sun and burns significantly less brightly than one might expect for a planet so close to its star, only 5% of the Earth-Sun distance, which might be expected to be a red-hot cinder. Because the total energy reaching Proxima b from the Sun is only 65% of what Earth receives, liquid water may readily persist as long as the planet had an atmosphere to retain heat in. While examining this star system, scientists discovered several unexpected anomalies in Proxima b. These anomalies, known as artificial lights, have perplexed the world's top scientists. But what exactly are they? Do these lights imply the presence of intelligent life on this planet? For years, scientists have been perplexed by these questions. As far as we can determine, the universe should be teeming with life. Furthermore, many of these aliens should be technologically advanced enough for humans to converse with them or pick up their radio communications. We haven't seen or heard anything yet, and the sky appears to be lifeless. Now that the James Webb Space Telescope is operational, we have access to totally new astronomical observation technologies. This telescope is powerful enough to view and image exoplanets, as opposed to merely inferring their existence as practically every previous telescope before it has done. What are your thoughts on these latest discoveries by the JWST? Tell us in the comments section below. Let us know what you think about the chances of JWST locating a habitable exoplanet in the next months.